Hi, hello friends. Welcome to Indian Tech Guru for you. In this video, let us learn about all pairs shortest path problem using dynamic programming. So to solve this problem, Floyd and Warshall proposed this particular algorithm. First of all, what is meant by all pairs shortest path problem? All pairs shortest path problem means we need to find out the shortest path for all the pairs that are in the given graph. So let us consider a directed weighted graph. Vertices are 1, 2, 3, and 4. From 1 to 2, the weight is 3. From 2 to 1, the weight is 8. From 2 to 3, the weight is 2. From 3 to 4, the weight is 1. From 4 to 1, the weight is 2. From 1 to 4, the weight is 7. So this is the given graph, and there is one more edge from 3 to 1. From 3 to 1, the, the cost is 5. So this is the given directed weighted graph. Here, all pairs shortest path means we need to find out the shortest path between 1 and 2, between 1 and 3, between 1 and 4. Similarly, the shortest path between 2 and 1, 2 and 3, 2 and 4. Like this, we need to find out the shortest path for all of the pairs. That's why it is called as all pairs shortest path problem. The solution for this particular problem is derived using the dynamic programming, in which we are going to divide the entire problem solution into number of sub-problem solutions and then find out the optimal solution. So this algorithm is proposed by Floyd and Warshall. So that's why it is called as Floyd Warshall algorithm. First of all, let us see how to solve this particular problem. To solve this particular problem, first of all, we need to define adjacency solution matrix. Adjacency matrix A power 0. So adjacency matrix A power 0 is defined as it contains the elements as the direct distances from one vertex to another vertex. That is, there must be a direct edge between one vertex to another vertex. So whatever the weight given in the graph, that will be the distance. So if at all there is no direct edge, then we are going to consider the distance as infinity. If there is no direct edge, then the distance is considered as infinity. So now let us derive matrix adjacency matrix A power 0. Adjacency matrix is represented by number of rows and columns because here there are 4 vertices. So it contains 4 columns and 4 rows. So now let us fill this particular A power 0 matrix. So what it says, so it is going to calculate the direct distances from one vertex to another vertex. So from 1 to 1, there is no direct edge. So, and we know that from that vertex to the same vertex, the distance is always 0. So that is why from 1 to 1 it is 0, from 2 to 2 it is 0, from 3 to 3 the distance is 0, from 4 to 4 the distance is 0. So this is fixed. And now let us calculate the distance from 1 to 2. From 1 to 2 there is a direct edge and the distance is 3. So note it down. From 1 to 3, there is no direct edge. So because this is directed graph, we need to consider the direction also. There is an edge from 3 to 1, but there is no edge from 1 to 3. So whenever there is no direct edge, then we need to consider the distance as infinity. From 1 to 4, From 1 to 4, there is a direct edge. So, and the distance is 7. So, note it down. So, next from 2 to 1. From 2 to 1, there is a direct edge and the distance is 8. Note it down. And from 2 to 3, from 2 to 3, there is a direct edge and the distance is 2. Note it down. From 2 to 4, 2 to 4, there is no direct edge. So it will be infinity. Next from 3 to 1, from 3 to 1, there is a direct edge and the distance is 5. Note it down. From 3 to 2, there is no direct edge. So that's why the distance is infinity. From 3 to 4, there is a direct edge and the distance is 1. And from 4 to 1, there is a direct edge, the distance is 2. From 4 to 2, there is no direct edge, so it will be infinity. From 4 to 3, there is no direct edge, so the value will be infinity. Like this, we have filled the values for a power 0, so which will be representing the initial distances between all the pairs of vertices. So, however, like this, we need to calculate a power 1, a power 2, a power 3, and a power 4. As there are 4 vertices, we need to calculate up to a power 4. So, to calculate these values, we will be implementing one specific formula. So, that formula is a power I comma j is equal to minimum of a power minimum of a of I comma j comma a of I comma k plus a of k comma j. So this is the formula. So using this formula, we can calculate a power 1, a power 2, a power 3, and a power 4 matrices. So whenever we calculate a power 4 matrix, that represents the minimum distances. So because we need to find out the shortest path, so the distances must be minimum for all the pairs. So whenever we find out a4, a power 4, then it is going to calculate the minimum distance. Because here we need to find out the a power 1, a power 2, a power 3, and a power 4. So let us consider this as a power k of I comma j is equal to minimum of a power k of I comma j comma a power k minus 1 of I comma j plus a power k minus 1 of k comma j. So this is the formula. Here also it is k minus 1. So to find out the a power 1, we need to have the values of a power 0. So as we already know the values of a power 0, based on which we can calculate the a power 1, and using the values of a power 1, we can calculate the values in a power 2. Based on the values of a power 2, we can calculate the values in a power 3. Like this, we can calculate. So the general formula is a power k of I comma j is equal to minimum of a power k minus 1 of I comma j. That is the previous value, comma a power k minus 1 of I comma k. Here k is the intermediate node. K is the intermediate node. Okay. Plus a power k minus 1 a power k minus 1 of k comma j, where k is the intermediate node. So this k value actually represents the power value. So a power 1, a power 2, a power 3, and a power 4. So now it means that now we can calculate a power 2 using the a power 0 matrix. So let us calculate a power 1. 1, 2, 3, 4. 1, 2, 3, 4. So whenever we calculate a power 1, then k value will be 1. What does it mean? 1 must be the vertex in the path. So whatever the path we are going to consider, one must be in between the path. So what does it mean? Whenever we are going to calculate a power k, then we need to consider the distance a power k of I comma j. Consider the distance from I to j, from I to j, using the intermediate node or vertex as k. K must be the intermediate node. So if at all, if we try to calculate a power 1, then the intermediate vertex or node must be 1. Okay, the intermediate node must be 1. So if the intermediate node must be 1, then from 1 to 1, 1 to 2, 1 to 3, 1 to 4, the starting node is 1. So that's why the values will not be changed for the first row. So whatever the values that are available in a power 0, the same values will be there, because it represents the minimum of a power k minus 1 of I comma j. So this must be as intermediate node. We are going to take the same values as in a power 0, that is 0, 3, infinity, 7. Similarly, as far as the columns are concerned, from 1 to 1, 2 to 1, 3 to 1, 4 to 1, what does it mean? 1 is the destination vertex. 1 is the destination vertex, but 1 must be the intermediate vertex, in between vertex. So, the first column values will be same, 8, 5, 2. Similarly, 1 to 1, 2 to 2, 3 to 3, 4 to 4 will be 0. That is fixed. Okay, these values are fixed in a power 1. So now we need to calculate the remaining values. Uh, using the in-between node as 1. So let us calculate from 2 to 3. From 2 to 3 as intermediate node 1. So this must be intermediate node. So shall we come from 2 to 3? So if you go from 2 to 1, 1 to 4, there is no path to 3. So that's why we are going to use the same value, 2 value, because the formula says that minimum of a power k minus 1. A power k minus 1 here, 1 minus 1, 0. A power 0 of I comma j, that is minimum of 2 comma. If at all there is a path using 1 as intermediate node, then we need to calculate this particular path, but there is no such node, so that's why keep this value as it is. Next, from 2 to 4, 2 to 4, so we can go through 1, 2 to 1, 1 to 4. 2 to 1 value is 8, 1 to 4 value is 7. 8 plus 7, 15. So now this value is 15, and this value is infinity. This value is infinity. So which is the minimum of infinity and 15? 15 is the minimum. So replace infinity with 15. So this value has been changed from a power 0 to a power 1. So next, from 3 to 2, 3 to 2, so intermediate node must be 1. 3 to 2, intermediate node must be 1. So 3 to 1 and 1 to 2. 3 to 1, 5, 1 to 2, 3. 5 plus 3, 8. So replace this infinity with the value 8. Next, 3 to 4. 3 to 4 using infinity node, intermediate node 1. So 3 to 1, 1 to 4. 3 to 1, 1 to 4. So 3 to 1 is 5. 1 to 4 is 7. 5 plus 7, 12. So this value is 12. But what about this value, direct value? 1. This is 1. So which is minimum, 1 or 12? 1 is the minimum. So keep 1 as it is. Next, from 4 to 2. 4 to 2 using 1 as intermediate node. 4 to 1 and 1 to 2. 4 to 1 is 2 and 1 to 2 is 3. 2 plus 3, 5. So this value will be 5, replace this infinity. Next 4 to 3, 4 to 3 using intermediate node 1, 4 to 1, and there is no direct edge to 3, 4 to 1, and there is an edge from 1 to 2 and from 2 to 3. So now intermediate node will be 1. So 4 to 1 2, 1 to 2 3, 2 plus 3 5, and 2 to 3 7. So the value here will be 7. Replace this particular infinity. So this is the a power 1 value, a power 1 value. Okay. So here we need to remember that 1 must be the intermediate node, but the path may be two edges or more than two edges also. For example, here we are using the path from 4 to 3. 4 to 3, there is no direct path. So we must calculate using the 1 as intermediate node. So 4 to 1, there is an edge. 1 to 2, there is an edge. 2 to 3, there is an edge. So we need to consider all the distances of 3 edges and add all the distances. So 4 to 1 is 2, 1 to 2 is 3, 2 plus 3 5, 2 to 3 is 2, 5 plus 2 7. Like this we are going to get a power 1. So similarly, we can calculate the a power 2, a power 3 and a power 4. So let us calculate a power 2. 1, 2, 3, 4. 1, 2, 3, 4. So whenever we try to calculate a power 2, then second row and second column are fixed from the previous matrix. Second row is 8, 0, 2, 15. And second column is 3, 0, 8, 5. These are fixed, and 1 to 1 0, 3 to 3 0, 4 to 4 0. So these are the fixed values, and we need to calculate the remaining values. So let us calculate from 1 to 3. Now the intermediate node must be 2. From 1 to 3. 1 to 3, intermediate node must be 2. So 1 to 2, 2 to 3. 3 plus 2, 5. So already infinity is there. So remove this infinity and place it as 5. Next from 1 to 4. 1 to 4 using the intermediate node 2. So 1 to 2, 2 to 3, 3 to 4. 1 to 2, 3, 2 to 3, 2, 3 plus 2, 5, 3 to 4, 1, 5 plus 1, 6. But already what is there? Already 7 is there. So but 6 is less than 7. So replace 7 value with 6. Next 3 to 1. 3 to 1, intermediate node as 2. There is no direct edge, so keep 5 as it is. 3 to 4. 3 to 4, intermediate node as 2. So there is no direct, there is no link from 3 to 2. So that's why it will be same as previous value 1. Next 4 to 1. 4 to 1, intermediate node as 2. There is no direct edge. So that's why keep the previous value as it is. Next 4 to 3. 4 to 3 using intermediate node as 2. So 4 to 1, 1 to 2, 2 to 3. 4 to 1 is 2, 1 to 2 is 3, 2 plus 3 5, 2 to 3 is 7. 7. Already 7 is there. So both are equal. So keep the value as it is. So this is the a power 2 matrix. So let me calculate a power 3 matrix. A power 3 is equal to 1, 2, 3, 4. 1, 2, 3, 4. So as far as a power 3 is concerned, third row and third column values are fixed. 5801 is fixed, this one, and 5207. 5207 is fixed, and 110, 2220, 3230, 4240. We need to find out the remaining values. Here the intermediate node must be 3. So 1 to 2. 1 to 2, intermediate node as 3. So 1 to 7 is there, but there is no link here. So keep the previous value. 1 to 4, intermediate node as 3. 1 to 4, intermediate node as 3. So 1 to 2, 2 to 3, 3 to 4. Link is there. So 3 to 3 plus 2, 5, 5 plus 1, 6. Already 6 is there. So keep the value as it is. Next, 2 to 1, 2 to 1. 2 to 1 using intermediate node as 3. So 2 to 3, 3 to 1. 2 plus 3. Sorry, 2 plus 5. 2 plus 5, 7. This value. So we need to calculate from 2 to 1 using intermediate node 3. So 2 to 3, 3 to 1. 2 to 3 value is 2. 3 to 1 value is 5. 2 plus 5, 7. Already 8 is there. Replace this 8 with 7. Next, 2 to 4. 2 to 4 using intermediate node as 3. So 2 plus 1, 3. Already 15 is there. Replace this 15 with 3 because 3 is minimum. Next, 4 to 1. 4 to 1 using intermediate node 3. There is no link. So keep the previous value as it is. Next, 4 to 2. 4 to 2 using intermediate node 3. There is no link. So keep the previous value as it is. So we have calculated up to a power 3. Now, before calculating a power 4, let me make some space here. So the final step is to calculate the a power 4, which will give the shortest distances between all the pairs. So let me calculate a power 4 here. 1, 2, 3, 4. 1, 2, 3, 4. So from a power 3, I need to calculate a power 4. So a power 4 means the intermediate node must be 4. Here the intermediate node must be 4. So and the fourth row and fourth column are fixed. Fourth row is 2570. 2570. It is fixed. Next, why it is fixed? Because 4 must be intermediate node. It must not be starting node or terminating node. And fourth column is 6310. 6310. It will be fixed. 1 comma 1 0, 2 comma 2 0, 3 comma 3 0. Now let us calculate the remaining values. So here the intermediate node must be 4. So next, 1 to 2. 1 to 2 using intermediate node as 4. 1 to 4, from 4 to there is no link. So keep the previous value 3 as it is. Next, 1 to 3. 1 to 3 using intermediate node 4. So 1 to 3 using intermediate node 4. There is no link here. It will stop here. So keep the previous value as it is. Next, 2 to 1. 2 to 1 using intermediate node as 4. So 2 to 3, 3 to 4, 4 to 1 is there. So 2 to 3 is 2, 3 to 4 1, 4 to 1 2. 2 plus 1 3, 3 plus 2 5. So already what is there? Already 7 value is there. 7 must be replaced with 5. Next, 2 to 3. 2 to 3 using intermediate node 4. So there is no direct link here, it breaks. So keep the previous value as it is. 2. This value is 3. Already there. Next, 3 to 1. 3 to 1 using intermediate node 4. So 3 to 4, 4 to 1 is there. So it is 1 plus 2, 3. So replace this 5 with 3 value. Next, 3 to 2. 3 to 2 using intermediate node 4. So 3 to 4, 4 to 1, 1 to 3. Sorry, 1 to 2. So 3 to 1, 1. 1 plus 2, 3. 3 plus 3, 6. Already the value is 8. Now replace 8 with 6. So with this, we have successfully completed a power 4. So a power 4 gives this matrix gives the shortest distance from all pairs, that is from 1 to 2, 1 to 3, 1 to 4, shortest distances it is going to give. From 3 to 1, 3 to 2, 3 to 3, 3 to 4, it is going to give the shortest distances. So like this, we can calculate all pairs the shortest path problem using dynamic programming using the Floyd Warshall's algorithm. Hope you understand the logic. Thanks for watching. That's all for now.